The metallic character will affect the melting point and boiling point of an element. So how are we going to recognize whether the element has a metallic character or not? The easier it is to remove electron from an atom, the more metallic the element. So metallic characteristic will decrease across the period because we are going from metal, transition metal, and non-metal element for P block. Okay, so going across from left to right, the metallic characteristic will decrease because we are going from metal to non-metal elements. For group 1 and group 2, the other name for it would be the alkaline metal and alkaline earth metal. Okay, for the non-metal, so we're just going to discuss group 17 and group 18, which would be halogen and noble gas. As you already know that metal, it will tend to form cation. But for the non-metal, it will tend to form anion. We're not going to discuss all elements for metallic characteristic in chapter 3. So the elements that are involved in this trend are the sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon gas. Make a note that for the sodium to aluminium, they are metal. They exist as metal. For silicon, it is a transition element, transition metal. From phosphorus to argon, they are in the non-metal group. Just highlight these 4 things: phosphorus, silicon, chlorine. Okay. These 3 elements, they do not exist as phosphorus, and sulfur does not exist as S2 or sulfur. And chlorine, you must write it down as Cl2, not Cl. Okay. So phosphorus S8 and Cl2, you must write it according to their stable state. So how does all the elements that I mentioned before different in their strength of attraction? Okay. For sodium, magnesium, and aluminium, they will exist as metal. For silicon, as transition metal. And for this group, they will exist as non-metal, as we talked before. For this metal, they will have a metallic bonding. So metallic bonding is directly proportional to the number of valence electrons. So this is going to be easy for you guys. Sodium, it has 1 valence electron because it is in group 1. Magnesium would be 2, and aluminum would have 3 valence electrons. So how are we going to arrange the melting point and boiling point based on this trend? Okay, so when the number of valence electrons increase, metallic bonding increase. So we're going to say aluminum has the highest metallic bonding because it has the highest valence electron. So aluminium would have the strongest metallic bonding, followed by magnesium, and sodium would be the last one with metallic bonding. For the transition metal, it will form covalent bond. So what's going to happen? That silicon, it will form a gigantic molecular structure just like this. So where each silicon atom is bonded tetrahedrally to another 4 silicon atoms. So what I mean by this is that, let's say we have this green silicon atom. It must be bonded tetrahedrally, means 4 to another 4 silicon atom. 1, 2, 3, 4. So these 3 orange silicons will bond it further with another 4 silicon atoms. So they will expand a lot more to form a gigantic silicon molecular structure. For the nonmetal, that would have the van der Waals forces. So van der Waals forces is directly proportional to the molar mass. So for the element P4, the molar mass would be 60. For S8, that would be 112. For Cl2, 34, and argon would be 18. So now we're going to arrange these van der Waals forces of nonmetal according to the melting point and boiling point. So which molar mass is the highest one for this nonmetal element? Okay, that would be S8. So S8 has the strongest van der Waals forces, okay, followed with P4, Cl2, and the weakest van der Waals forces would be exerted by argon. Okay, because we all know that this comes from group 18 element, which is non-active or non-reactive compound. For silicon, that would be just Si itself, because we don't compare it with other transition metals. Now we have to arrange this metallic bonding, covalent bond, and van der Waals forces according to the strength of attraction. So the strongest one would be the metallic bonding, followed by the covalent and the van der Waals. So you just have to arrange the element like, okay, with a big arrow going to the right, indicating the strength of attraction decrease. The last thing in chapter 3 is to know the oxide of period 3 elements. So for the metal, sodium, magnesium, it will form a basic oxide. Okay? Because when sodium reacts with H2O, it will form sodium hydroxide. So this hydroxide, which is the OH minus, it exists as a base, right? So sodium and magnesium will form basic oxide. For the aluminium, it would form amphoteric oxide. What does it mean by amphoteric? It can act as both acid and base. For the non-metal elements, it will form acidic oxide. They are acidic oxide because for example, when phosphorus reacts with water, it will form phosphoric acid, okay, which has a H plus in it. Okay. H plus has an acidic character, so these are the acidic oxide. In short, in order to determine the oxide of period 3 element, you have to write the equation between the metal, the amphoteric, and the non-metal reaction with water first. And then you have to figure out whether OH minus or H plus is being produced. Okay? If OH minus is produced, then metals, the sodium and magnesium will form basic oxide. And for the non-metal, okay, it releases hydrogen ion in the product, so they will form acidic oxide. Okay, for amphoteric, it depends on your equation. If you want the AlO3 to be base, then you have to react with acid. But if your AlO3 is an acid, then you have to react with a base. And the product and side product would be different as well.